The Winkler Method and Biochemical Oxygen Demand. These are a couple of environmental chemistry topics that are actually in the redox part of the chemistry syllabus. They're there because the reactions involved are technically redox reactions, but actually, as it's generally going to be asked about or used on the exam, it's more of a stoichiometry and titration topic. So that's why we're going to cover it now. The Winkler method is an example of where you want to analyze something, in this case oxygen, dissolved oxygen, but oxygen is not something that's very easy to titrate for directly, test for directly. So you first have to react the oxygen with something else. So there's sort of a series of chemical reactions, and the final reaction is the titration. And so you're kind of indirectly going to figure out how much oxygen was in the original sample through the titration. Okay, so first we have to talk about dissolved oxygen. So oxygen, O2, the stuff that we breathe, can dissolve in water to a certain extent. The concentrations are generally quite low, and so these concentrations are usually expressed in parts per million, ppm, which is the same as milligrams per liter. So these are very small concentrations, so if they were in moles per dm cubed, they'd have a number of zeros in them, so 0.000, for example. And so parts per million is just a different unit of concentration that makes the numbers simpler when we are describing those low concentrations. But this dissolved oxygen is critical for aquatic life. It's how fish breathe, is by their gills actually are able to remove that oxygen from the water, and that's how they're breathing while underwater. Another term that comes up is the biochemical oxygen demand. So in a body of water, there are organisms that are using that dissolved oxygen. Now, normally in a healthy ecosystem, that oxygen is being replaced by photosynthesis, by aquatic plants that are producing oxygen. And so the amount of oxygen stays about the same in that body of water. But if you want to test for this biochemical oxygen demand, which is how much oxygen is being used by the creatures living in that sample of water, what you can do is you can measure the concentration of oxygen in the sample, and then you can place another sample in the dark. And because if you place it in the dark, that will essentially shut down the photosynthesis that's taking place. And so a few days later, you should see a decrease in the concentration of oxygen. And so that change in the concentration of oxygen, and it's going to be, should be a decrease in the amount of oxygen since you've essentially shut down the photosynthesis. That change in concentration is what's known as the biochemical oxygen demand. Now, like I said, in a normal system, the oxygen gets replaced by the photosynthesis, but we're kind of forcing photosynthesis to stop, and therefore we'll see this drop in oxygen concentration. Now, at the same time, the IB brings up the topic of eutrophication. It actually is a very important concept to be aware of. It's related to, especially to fertilizer use. Eutrophication happens when we overuse things like nitrates and phosphates in our fertilizer, and those dissolve in water and they end up in bodies of water, like oceans, or they could be in lakes, but usually this is in oceans where rivers are dumping into them. And if you dump these fertilizer compounds, nitrates and phosphates, into a body of water, it will essentially fertilize the aquatic plants, particularly the algae, and it will cause these huge amounts of algae to grow, and they call these algal blooms. And so you create tons and tons of algae, sort of an unnatural amount of algae, which when they die, those algae start to decay, and the bacteria that break down the algae that break down all the bodies that do the decaying of the organisms, they remove oxygen from the water. And so as a result of all these excess fertilizers, nitrates and phosphates, and all this excess algae growth, eventually you get a situation where the concentration of oxygen is brought down so low by all the decaying algae that's being broken down by these bacteria that the water becomes unlivable for most aquatic life. And so this process, where we are dropping the concentration of oxygen to basically unlivable levels, is the eutrophication process. And so it's just, we're tying it into the environmental chemistry. I don't think you need to really know about eutrophication for the exam, but it links to this biochemical oxygen demand. Okay, so where's the stoichiometry? So in the Winkler method is essentially a way to fix the oxygen, because since oxygen is normally a gas, it actually leaves its dissolved state, this aqueous state, fairly easily. If the water gets warmer, more of the oxygen will leave. If you can shake the solution, and that can actually put more oxygen into it. So it's quite unstable, this concentration of oxygen. So when you take a sample of water and you want to test for how much oxygen is in it, you first want to add something to the water that will react with the oxygen and sort of fix it. So that's what this reaction number 1 is. You add a compound that has manganese 2+ ions in it, and those react with the oxygen and they sort of fix it. They fix the oxygen, which means that now the oxygen is locked up in a compound. So the oxygen won't leave the solution if it gets warmer, for example. Okay, that's our first step. And the second step is we're also not going to titrate for that manganese dioxide, though. We're going to take this manganese dioxide compound, and we're going to do another reaction with some iodide ions present and some acid present. And that will cause that manganese dioxide to dissolve, and it will make some iodine. Now, why do we want to make iodine? The reason is because iodine is actually something that's fairly easy to titrate for, and it stays dissolved in the solution easily. So in step 3, we react the iodine that we made in step 2 with this ion, which is called the thiosulfate ion. And it produces iodide ions and another ion. That's not really important. But the point is, this last one is actually the titration. So we want to know about this oxygen that's way back here in step 1, but we're not actually reacting with it directly. But through the power of mole ratios, we can figure out the overall mole ratio between the thiosulfate and the oxygen. And the way that I do that is I kind of follow the molecules that are the same in both in 2 reactions. So this one. So if you can see that the MnO2 is a product of the first reaction, and then we're carrying it down to reaction number 2, and we're using it in reaction number 2. So the trick here, I think, is to make sure that the coefficients are the same in both reactions. So in the first reaction, we make 2 MnO2. So I'm going to bring that down, and I'm going to double all the coefficients in this next reaction so that they're consistent throughout both reactions. So 2 and 2. This H2O was actually supposed to have a 2 originally, so now I'm going to make that a 4. That was a typo on my part. Okay, now I'm going to do this again between reactions 2 and 3. So one of the products of the second reaction is I2, and that's what we end up titrating for here in the final reaction. But once again, the coefficients don't currently match, so I have the 2 here from this I2, so I'm going to make this one 2 as well. If I make that 2, I'm doubling it. I have to double all of the coefficients so that the equation is still balanced. And now what I can hopefully see, let's use one more color, is that if I follow these ratios through, what it tells me is that for every 1 mole of oxygen, I can see the coefficient in front of the O is a 1. So 1 mole of O2 makes 2 moles of MnO2. I take those MnO2 down here. 2 moles of MnO2 makes 2 moles of I2. And 2 moles of I2 reacts with 4 moles of thiosulfate. So in the end, the ratio between O2, the thing I'm trying to figure out, and the thing I'm adding in the titration, thiosulfate, is 4 moles of thiosulfate. So when I do my titration and I get, I know a concentration and a volume for thiosulfate, the thing I'm adding from the burette, I'll get the moles of thiosulfate, and I'll set up a little mole ratio that it takes 4 thiosulfates for every 1 O2. So I'll plug in my number here, and I'll be able to solve for the moles of O2 here. So it's complicated using these series of reactions and doing a titration on something that actually you don't really care about. You don't really care about the amount of iodine, but you can use the amount of iodine that in reaction 3, and through that you can know the amount of MnO2, and through that you can know the amount of O2. So we're titrating for something indirectly with the Winkler method. And the Winkler method is all about oxygen and looking at biochemical oxygen demand, which is how quickly oxygen gets used up or decreased in a system.